So you did Newton's divided difference. It interpolates a polynomial. So if I draw a picture of what Newton's divided difference does, you have several points that you want to interpolate, right? So this is x, this is y, and your function looks something like this. Could look something like this. And then you want to interpolate a polynomial. Something like this. Right? Now it turns out that this is not a very good method. Often you do some interpolation like this, and something that looks fairly reasonable, and then out here it goes wacko. Usually it goes wacko out here. The same reason for Taylor series. If you've ever seen Taylor series for sine, I think we actually did this, didn't we?
Mm-hmm.
So
Dr. Kaw makes a big deal about once you get your equation, it's only for that interval. It's not.
Yes, it's very limited.
Yeah.
Okay, so this is a similar problem. I can just say it. It goes wacko far away from the expansion point. Okay, right. So you can see. So you can look at Taylor series for sine. I think we actually did this, didn't we? You saw a Taylor series for sine. It's good, okay, and then once it goes bad, it goes really bad. Okay. So the solution is not to try to do something smooth that approximates everything, but approximate by piece. So you can say approximate locally by polynomials in small intervals. Okay. So, for instance, if I have points here, here's x and here's y, and suppose I have evenly spaced points here, right, and my values are like this. What I do is I do one quadratic here. I can do a quadratic there, so that would be one quadratic. Then I do another piece here, and then I do another piece here, and then I should have done a different color. I don't think it took. I do another piece here, and then I do another piece here, and these are all different polynomials, but they fit together.
So it's kind of like a piecewise.
It is. It's exactly piecewise. So these are all different polynomials. So to use a different polynomial on each interval, but they fit together smoothly. And what does smoothly mean? It's continuous and continuous derivative. All right. So what this does is these conditions produce a system of equations for the coefficients, for the polynomial coefficients. Okay, which can be solved using matrix methods. Okay. So you can imagine if each one of these has a different polynomial. Suppose this had a quadratic polynomial here. That's three coefficients there. Three coefficients here, three coefficients here, three coefficients here, three coefficients here, 3. 1, 2, 3, 4, 5, 6, 6 times 3, 18 coefficients you have to solve for. So you have a lot of equations, but with a computer, 18 equations is nothing. It's nothing at all.
So we don't worry at all about what order would be best. It's just always quadratic.
No, actually, cubic is better.
Cubic.
Cubic is much better. So, but he doesn't do cubic. So I think we probably end up just doing quadratic. So let's look at and see what he does. How he sets this up. All right, so here he's saying the same thing. You see, he's saying we have data points here, and you're talking about interpolation, and then he talks about extrapolation, and here he says this stuff here, and he says so you see, here's an example, right? He does this. Tries to use a smooth polynomial to interpolate this Gaussian function, and then like this is a 12th order polynomial. See how wild it becomes out at the tails. So you want something. So instead of doing this, you approximate it piecewise. You don't try to get one function that approximates the whole thing. So linear spline is a very easy idea. You just do a straight line between them. Now, if you do straight lines between points, there's no way that you're going to be able to get a continuous derivative, right? How can you? Because this line, these 2 points determine the line, right? These 2 points determine a line. If they're not lined up, you're out of luck. There's no way that this is going to be smooth. So the nice thing about quadratic is you can make the derivative smooth. So I think he has and so he has the system of equations there. So here's quadratic. So quadratic means that on each interval you have three. This is just like I said. On each interval you have three coefficients that determine a quadratic, and you're going to have a system of equations that for all of these variables. So if you have n variables, you have 3n constants to solve for. Right? And you can see what some of the equations are. For instance, when at x1, the value of this function has to agree with the value of this function. So that means a1 x1 squared plus b1 x1 plus c1 equals a2 x1 squared plus b2 x1 plus c2. That's one equation. Now that's a linear equation. It looks like it's not linear, but it's linear because the x's are known and the a, b, c is unknown. So notice the equations are linear in the coefficient. So you can, if it's a linear equation, you can set it up as a matrix equation. So you're going to get a bunch of equations. I think he summarizes them down here. You see, here it says 3n unknowns have to set up 3n equations, right? All right. So here's his first set of equations. Each one of these has to agree with f. Here's having each one agree with f at the left-hand endpoint. Right. For instance, this first equation holds on the first integral from x0 to x1. So this agrees with f at its left-hand endpoint, and so does this one all the way down here. Then he's going to have a system of equations where they agree with the right-hand endpoint. Okay. So then he says this condition gives 2n equations because each equation has to agree on the left-hand endpoint and the right-hand endpoint. So you need another n equations. Then he gets these derivative conditions that the derivative of the first equation is continuous with the derivative of the second equation at the point where they join. The first two join at the point x1. So you have to set this derivative equal to this derivative. Okay, so that's going to give you another set of equations. Okay, and then that gives you another n minus 1 equations. So you're one equation short. And the other one equation short is you just assume the first spline is linear. So you just set the quadratic term equal to 0. So that gives 3n equations. So the whole idea is you need to set up some big matrix based on the values of the function, and then solving the matrix. It's really quite easy to solve a matrix in Python. There's a single statement to do that. The hard thing is actually setting up the matrix. So what I'll do is I'll give some guidelines on how to set up this code, and then that's what you can do for this week to do this code. And I'll see if I can get you to do cubic splines because that's really what is really actually used. But this is a good practice. Okay, so that's what I wanted to say. I can stop the record.